Hello everyone, good evening. So if you remember, yesterday we had seen about the artificial neural network, and today we'll talk about the convolution neural network. Yeah. So this convolution neural network is very effective whenever we have to deal with the images. Yeah. So this, in another words, I can say that this convolution neural network is used whenever we have to deal with the images. Okay. So let me show you. So let's talk about this convolution neural network. And so we are just going to discuss how this computer reads and images, why we will not use the fully connected whenever we'll have to deal with the images, and what is this convolution neural network and all. So suppose this is my image, yeah, and this is the colored image. So if you have to represent it, then this will be represented by the 3 dimension, where the first 2 dimension will be the first 2 dimension will be talking about the height and width of the image, and the third dimension will be talking about the color. If you are saying here B cross A, where B is the what? The height of the image. The A is what? It is the width, and the 3 is containing this 3 is saying that we have the color having RGB channel. When this will be 1, it means it will be the grayscale image. So either we'll have the colored images or grayscale images. So why do we not use it? Because if you are using this 228 by 28 by 3, that means what? If you multiply it, then it will become 2352. So this 2352 will be the weight will be updated in the first hidden layer. Yeah, this will be the number of hidden weights that needs to be updated in the first hidden layer. Okay, but in the real scenario, we don't have this less size of the pixel. We may have the pixel size like 200 by 200 by 3. That is 1,20,000. So if you'll have one image, and if you have to update the weight of it, then you will have to update this 1,20,000 weights. And suppose your data consists of multiple images. Say that 10. That means 10 times you have to update the 1,20,000 weights in the first hidden layer. And the thing is that you may have multiple hidden layer in your data, in your neural network architecture. So that means you can imagine that how much time it is going to take just to update your first hidden layer and the multiple hidden layers. And that is why whenever we have to deal with these images, we never used to work with the artificial neural network. We used to work with the convolution neural network. So this is the convolution neural network. And what this convolution neural network says that, for example, you please consider this brain. Just to visualize this, visualize any object. Okay, someone is. For example, just to visualize an object, there's a visual cortex in your brain. So when your eye visualize an object, this is decided by what? This visual cortex of your brain. And in the same way, you see, for example, this is your brain. It is divided into the left lobe and the right lobe. And you know that if you're doing any arithmetic calculation, then I'm not sure, I don't remember. Either your left lobe or right lobe will be taking participation here. Your entire brain will not be taking participation. In the same way, if you'll be doing the reasoning, then your, I don't remember, I think right lobe will be taking participation. Means your entire brain will not be taking participation. But if you would have implemented this concept using the artificial neural network, then what would have happened? That your entire brain was taking participation to work on the arithmetic calculation, although only the left lobe was needed. So that's why your convolutional neural network says that, suppose if I have to connect with the first hidden layer, and just to work with this node, only these three nodes are required to be connected, or only the weight of these three nodes are needs to be updated. Then why to update the weights of the all the node? Yeah, if just to work with this, only the weight of these three nodes are needs to be updated, then why we require to update the weight of all? And obviously, just because of that, what will happen? The time that it was taking to implement using the artificial neural network, it will become very less. Yeah. Friends, once again. Next. So whenever we work with this convolutional neural network, actually we use these four layers. This convolution layer, this ReLU layer, pooling, and the fully connected. And I tell you one thing, that whenever you have to work with this convolution layer, you can repeat it for multiple times. Means this convolution, ReLU, and pooling will be repeated for the multiple time. This fully connected is used for once. This fully connected is used for once. Let's take a problem where your convolution neural network will be trying to identify whether the input that you have used, the input that you have entered, the input image that you have entered, is it X or O? Means your convolution neural network model is going to be trained on the X and O. And after that, once any input will be given, then it will be easily identifying that whether the input image is X or O. Okay. Next. So, you know that whenever you'll be training your model, then you're not going to get same images. You might get a very good image, or you might have the distorted image just like this. But when you'll be say that you are inputting this kind of image, still your model should be able to recognize that this is the X. Yeah, because although might be the accuracy will be little bit less, but yes, your model should be able to classify it as X. Means This should be equals to X, this should be equals to O, although they are not 100% similar. Here, what we are going to do, suppose this is my X. This is my X. So wherever the X pixels are used, they're going to represent with the black, and they will be giving the value as 1. Whichever pixels we have not used, they will be represented as -1. Okay, and you see this is the 9 by 9 pixel. So whenever we'll be applying a normal technique, what will happen? Say this is the image on which you have trained, and this is the input image. When you do comparison, the resultant image, your model will be considering this one, and that will be easily considered as X. So whenever your image needs to be classified, then before that, your model will get trained. And how this model will be trained, or if I ask you that suppose these are the two images. These are the two images. Are they same or not? Are they similar or not? How you identify here? So you will just get each individual feature. You will just compare this left eye with the left eye of the images, this right eye with the right eye of the images, this mouth with the mouth. Okay. And on the basis of the percentage of match, you will say that whether these two images are similar or not. These two images are similar or not. Okay. So in the same way, what will happen when we'll be representing this image in the pixel? We'll just try to get some, individual pixels. We'll be trying to get some individual features, and that features will be called as filter. So say that we are using the 3x3 filter. And if I talk about this 3x3 filter and say that we are using only 3 filters. So we are using 3 filters, means we are going to check the images on the basis of 3 unique features, and the size of these three will be of what? 3x3. Let's say that the first size we took this one. Okay, and can I say that this is same like this one? Yeah, in the same way, this is the 3x3, and this is same like this one. So the upper left is equals to the down right, or the bottom right. The upper right is equals to bottom left. And the another feature or the filter we are using, that is what? That is this one. You see? So in this case, we have taken 3 unique features, and the size of these features we have taken 3x3. All right, next. You see? We have taken this as one filter, this as second filter, and this as the third filter. Now what we will do, we will have these 3 filters. If you remember, this is the same. So this middle one is actually representing the the feature that will be showing the central value of the image. This one is showing the one half of the left half of the image, and this one is showing the right half of the image. So we have used 3 filters. Now what we will do, we were using this convolution, the ReLU, and the pooling. As I told you that the fully connected layer will be using for only once. Okay, now here I will just match the entire image with this filter. The purpose is first to reduce the size. Okay, so we'll just work on the convolution, and each filter will be compared with all the data of the image. And since the 3x3 filter is there, so we'll be doing comparison also by imposing it, superimposing it on the 3x3 pixel size of your images. Okay, and we'll see. Yeah. So let's talk about this convolution layer. Here, the purpose is first we'll be line up with the feature and the images, and then multiply each image pixel by the corresponding feature pixel. Let's talk this one. Okay, let's talk this one. So we'll just take the print the screen of this. We'll go here. Please try to understand. So we are into this convolution, and let's talk about the first filter. Let's talk about the first filter, and this is our first filter. So we'll try to compare it. We'll try to just move it on the entire image. Let's say that we have taken here and we have superimposed on it. We have superimposed on it. And then what we'll do, see, this pixel will be multiplied with this pixel because it will be somewhere covering this by this. So 1 into 1, yeah, 1 into 1 is what? 1. Let me write here. 1 into 1 is 1 plus minus 1 into this minus 1. It will become 1. Then minus 1 into minus 1. Again, it will become 1. Then minus 1 into minus 1. It will become 1. 1 into 1. It will become 1. Minus 1 into minus 1. It will become 1. Minus 1 into minus 1. It will become 1. Minus 1 into minus 1. It will become 1. And 1 into 1. It will become 1. So how many times we have multiplied? So 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. And you will just divide it by 9. So what you got? You got 1. You got 1. So this 1 will become, so you are again going to, like you will have this, so when you'll be representing this, that will be representing the central value. So the central value will become 1. Say that you're again roaming this, and you have started to went here. Now you just shifted your filter by 1, and you went here. Now again, what will happen? So this 1 will be multiplied this minus 1. It will become minus 1. This minus 1 will become multiplied with the minus 1. It will become 1. This minus 1 will be multiplied with this minus 1. It will become 1. This minus 1 will be multiplied by this 1. It will become minus 1. This 1 will be multiplied with this minus 1. It will become minus 1. This minus 1 will be multiplied with this minus 1. It will become plus 1. This minus 1 will be multiplied by this minus 1. It will become plus 1. This minus 1 will be multiplied by this 1. It will become minus 1. 1 will be multiplied by the minus 1. It will become minus 1. And how many total values are there? So it is 9. So it will be divided by 9. You know, this will be cancelled by this one. This will be cancelled by this one. This will be cancelled by this one. Yeah. In this way. And you know, this will be cancelled by this one. So you got minus 1 upon 9. Guys, what will be the value here? Please tell me when you divide it. Minus 1 upon 9. What will be this value?
minus
Sorry,
0.11.
minus 0.11.
minus 0.11, isn't? That means when you have superimposed this onto this, so it will become the central value for this 0.11. In the same way, suppose you are superimposing this on the center. So can I say that this is the center of the image? Yeah. Again, what will happen? So you'll be multiplying this one with this one. So it has becomes 1 plus minus 1 into minus 1. It has become 1. Minus 1 into 1. It has become minus 1. Minus 1 into minus 1. It has becomes 1. 1 into 1. It has becomes 1. Minus 1 into minus 1. It has become 1. Minus 1 into 1. It is minus 1. Minus 1 into minus 1. It is plus 1. 1 into 1. It is plus 1. Upon again 9. So, this will be cancelled by this one. This is cancelled by this one. So 1, 2, 3, 4, 5. 5 upon 9. What is the value here?
0.55.
0.55. Yeah. So in this way, we are going to get a new, the table where we'll be having these values. Let me show you. You see, we got the center value. Yeah, we got this 0.55 if you remember for the central. So we got here 0.55. In this way, we have just moved our filter to each portion of the images and we got this value. So this is when we had moved our one filter to each portions. And you see, if you remember guys, this right to the one we had minus 0.11. Can you see? So when you will be moving this filter to all over your images, you are going to get this value. Yeah. Since we have 3 filters, so I can say that after doing this convolution, we are going to get 3 different tables. I hope you understand how this convolution layer has worked. Yeah. So this is your convolution layer. And next to this, what you are going to do, you will have the ReLU. And what is the job of this ReLU? Whatever negative value will have, we'll just make it as 0. You see, if your f of x is equals to, if this f of x is equals to 0, when the x is less than 0, and your f of x will be equals to x when the x is either greater than or equals to 0. Means the positive value will remain same, otherwise the negative value will become 0. So you see, wherever you had the negative value, like in this first row, this minus 0.11 and this minus 0.11, they will become 0. Here in the second row, this minus 0.11, this minus 0.11, this minus 0.11, this minus 0.11 will become 0. Here, this minus 0.11, minus 0.33, minus 0.11, they will become 0. So what I mean to say that wherever you'll be getting the negative value, they are going to make it as 0, just like. See? Okay. And since again, I'll tell you only one thing, that we have how many filters? We have how many filters? 3. We had 3 filters. So the same ReLU will be applied for how many times? 3 times. How many times? 3 times. You see. So wherever we had the negative value, it has becomes 0. Then let's come to this pooling. Again, the purpose of using this pooling layer is to reduce the size by 50%. Yeah, just to reduce the size by 50%. Okay. So, first of all, try to understand here. Just to apply this pooling, we pick some window size, and that window size is usually 2 or 3. For our case, we'll be taking 2 by 2. We'll not be taking a 3 by 3. We'll be taking a 2 by 2. Then we need to take the stride, and the stride will be taking usually 2. We can take 1, we can take 3, but in our case we are going to take 2, and we'll be walking our windows throughout your filtered image, the 7 by 7 image that you got after convolution. Okay, yeah, and then from each window we are going to take the maximum value. We'll do it. So say that this is my first filtered image. This is my first filtered image. So what I'll do, I'll just take the screenshot of it. We'll paste here. Okay. So as we have told that we'll be taking the 2 by 2. Okay. And the stride value will be 2. So let's say that 2 by 2. So we just took this 2 by 2 and we are moving this 2 by 2 window. So first of all, we just went here. And the maximum value is what? The maximum value is 1. So we'll be keeping 1. Then we'll just take a stride value of 2. So let me write it as 1, 2, 1, 2, 1, 2, 1, 2. So after 2 will start. So that means we'll be starting from here. Again, take 2 by 2. Again, in this, what is the maximum value we have? 0.33. Then after, since again 1, 2, so 2 gap, straight means the gap we are going to take. So we'll be starting from here. Yeah, we'll be starting from here. And what is the maximum value we have? It is 0.55. Then after, we have to take the 2 by 2. We have to take the window size 2 by 2. But the thing is that we have only 2 by 1. We have only 1 column and 2 row. But according to our requirement, we should have 2 row and column. Yeah. So just to fulfill that, what we will do, we'll just add another column. We'll just add another column, and we'll give the value here as 0. This is called as padding. Adding either the extra row or the column, it is called padding. Stride means whenever you are moving this window, taking the gap. So now you see the maximum value is what? 0.33. And now we have moved to this window column wise. Now we'll move the row wise. Again, we'll take the gap of 2. So 1, 2. We'll be starting from where? We'll be starting from here. Yeah. So again, what is the maximum value? It is 0.33. Then we'll move here. So what is the maximum value? 1. Then again, the stride of 2. This is the value. So it will become 0.33. Again, you see, we have to get 2 by 2 and we're getting 2 by 1. It means this for the last column, we're going to face this problem. Means for the last column, we are going to add 1 extra column. And this extra column will be filled with the value 0. Okay. Now we got this 2 by 2. And in this 2 by 2, we have 0.55 as the maximum value. In this way, again, the stride value of 2 for the row wise, and we got here. Yeah. The maximum value is what? 0.55. Then here it is 0.33. Then here it will be 1. Then still it will become 0.11. Yeah. Then after, you see, Again, if you are taking the style value of 2, we have only one row remains. Means we have only the one row. Means we will have y2 shape. And we require 2 by 2. So just to do that, what we will do, we'll add one extra row. So we have done the padding at the row side. So 0, 0, 0, 0, 0, 0, 0. Now, if I take the first two window, so what is the maximum value? We have 0.33. Now we take this window, so we have 0.55. We have this is 0.11, and it is not 1.77, it is the 0.77. So we got here 0.77. You see, so when we have applied this pooling, can you see whatever the size of the image was, that was 7 by 7, it got reduced by its half, almost 4 by 4. I hope that is clear. Okay, so this is the 4 by 4. Now, we have applied this. Okay, we have applied this. You see, so this value we got, we have just applied the ReLU at one filtered image. In this way, we'll be applying this ReLU at the all these three. And you see this convolution ReLU pooling we had applied for the 2 times, and we got, so I can say that initially here we had 9 by 9. We applied this ReLU, we applied the pooling, and we got here 4 by 4. So this 4 by 4 will be passed to this convolution. Again, we'll be applying ReLU, and then this 4 by 4 got reduced by half, and it has becomes 2 by 2. Yeah. Okay. Now what we have done, these were the outcome of the first filtered image. This is the outcome of the second filtered image, and this is the outcome of the third filtered image. So we just represent this 2 dimension into 1 dimension, and that is the job of what? Fully connected layer. And here what exactly we are doing? We are flattening it. We are flattening it because the classification we are going to do at this layer. And this fully connected layer is what? It is actually your artificial neural network. Okay, so we have just stringed here, and we have just represented them into a 1 dimension. So this 1 is there, this 0.55 is there, 0.55 is there, 1 is there, 1 is there, 0.55, 0.55, 0.55, 0.55, 1 is there, 1 and 0.55. So this is the final outcome at the fully connected layer when your model got trained in for the X. In the same way, when your model will get trained on the O, this will become the single dimension. Now, if I see here that where the maximum value in case of X, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. When the model was trained at X, on the X, it found that the highest value, that is 1, is at the 1, 4, 5, 10, and 11. You see? So 1, 4, 5, 10, and 11, this is the place where the value of value is 1. Yeah. So let me note it down. So I can say that for the 1, we have the value at 1, 4, 5, 10, and 11. In the same way, if I find out for the O, then I can say that this is at 2, 3. 9 and 12. You see, 9 and 12. So in case of O, that is 2, 3, 9, and 12. 2, 3, 9, and 12. This is where your values are maximum. Now, suppose you entered this image. You input this image, and obviously this image will go for the convolution, ReLU, pooling, yeah, and the fully connected layer. And after that, you got this one. You got this one, and you just try to identify whether this input image that you have done, it is the X or O. It is the X or O. Okay, so let me check it for X. So when I'll be checking it for the X, so for the X, we had the value maximum or the highest at the 1, 4, 5, 10, and 11. Yeah. So at the 1, what is the value? That is 0.9. At 4, what is the value? That is 0.87. At 5, what is the value? It is 0.96. At the 10, what is the value? It is 0.89. And at the 11, it is 0.94. So there are 4 values, no? 1, 2, 3, 4, 5. 5 values are there. We'll just divide it by 5. Everyone, please tell me what is the value. Please tell me.
0.91.
0.91. Yeah. 0.91. And if I multiply with this 100, then I can say 91% it matched with the X. Let's talk about the O. So for the O, the value was maximum at 2, 3, 9, and 12. So at 2, what is the value here? It is 0.65. At this 3, what is the value we have? It is 0.45. At the 9, what is the value? That is 0.44. At 12, it is what? It is 0.53. Since 4 values are there, so we'll just divide it by 4. What is the value here, everyone?
0.51.
0.51, huh? And again, if I multiply with this 100, then I can say that it is 51%. So I can say that this input image is matched with X by 91%. With the O, it is only 51%. So obviously, your convolutional neural network model is going to classify this input image as X. I hope you understood now, isn't? So in this way, your convolution neural network classify your image. Okay. All right then. So let's see the implementation of it. So we'll just open the Google Colab. And friends, one more thing. On Saturday, I'm going to discuss the project. I'm going to check the progress of the project. On the Saturday, I'm going to check the progress of the project. So everybody, please prepare. Let me upload this file. CNN. Okay. So let me connect this. Okay, so the RAM is connected. We are again importing the layers and the model just like we have used in the previous, in the ANN. Now this is my model. Okay, this is my model. Let me define it. So here we are using the sequential model. So first of all, what is the size of our image? That is 28 by 28 by 1. That is 28 by 28 by 1. Then after, we have used the 32 filter using 3 by 3 size of each. So we have used 32 filter. And what is the size of each filter? 3 by 3. Then we have the ReLU. Then we have this ReLU. Okay. And after this ReLU, we have pooling. And for the pooling, you see, what is the window size we have taken? 2 by 2. So this is our pooling. After that, in the next time, what you have used the 64 filter, and each filter will have size of 3 by 3. Then you have this ReLU, and you have this pooling. Okay, then after again, what you did, and what is the size of this pooling window? That is 2 by 2. Then again, you just use this convolution, and what is the size? That is 64 of each, and each filter will have size of 3 by 3. Then you have the ReLU. So this is the architecture of your CNN model. Now you say how we have used this architecture. So my dear friend, defining the architecture, whether in the case of the artificial neural network or in the case of convolutional neural network, it is experimental. It is experimental. You'll be trying with the different filter size. You'll be trying with the different, the window size of the pooling. You'll be trying this. Okay. Yeah. So this is the architecture that we have used here. Next. After this, once you have defined the architecture, you had the convolution layer only. And one more thing you see, when you are using this convolution, initially you got the 26, means at the x and y, you had the one subtraction, isn't? Then the filter size of each is 3 by 3. But 3 by 3 has been 9. Why it has been 320? If you multiply with this 32 by 9, it will become something that will not be equal to 320. But when you work it, so it is y equals to mx plus c. So you have taken this, whatever the c part, bias. So that's why one weight that was updated for the bias, and it has becomes now 10. So 3 by 3 plus 1, it has become 10. and you multiply this 32 by 10, it will become 320. Second thing you see that when we had used this, after each convolution, the size is being reduced by 50%. Here it was 13. Again, 2 will be subtracted at each end, so it was 11. And again, after this pooling, you got 5. Another thing you see, the parameters are updated only at the time of the convolution, not at the time of the pooling. Yeah. And total, if you will add it, so how many total parameters were updated? 55,744. Next. So this is my fully connected layer, which is the artificial neural network. And if I see, just to apply this fully connected layer, we are calling this flatten function. That is, just flatten your 2 dimension into 1 dimension. Then you see we have added only one hidden layer. So this is my what? This is my one hidden layer. And that is what? It is my output layer. Since we are going to work on the MNIST data, which is the 10 class classification, because the handwritten digits or the digits are 0 to 9. So that is why, in the output layer, we have taken the number of neurons 10. The activation function equals to soft neurons. Okay, if you run now, so this where we have specified and we have specified our CNN architecture. And after that, let's read the data. So here, let me take again a screenshot of it. Let's check it out. We are importing this MNIST data, which is the handwritten digit. And we are again using from tensorflow.keras.utils, we are using this 2 underscore categorical, which will actually represent your number into categorical. So we have this MNIST data, and that MNIST data. So basically, this Keras will have lot of data sets, inbuilt data set. If you want to check it out, then you can check it out. So the Keras data set. You see? So these are the different inbuilt data set in the Keras, MNIST digit classification, CIFAR10 small images classification, CIFAR 100. So you can load these data, like Boston house pricing, fashion MNIST, Reuters, Newswire. So these are the different data sets you have. Out of that, we have used MNIST. Okay. Then this MNIST data that we have, it consists of 70,000 images. That consists of the 70,000 images. Out of that, what we have done, we have splitted them into train and test. Train and test. By default, if I ask you, there's total 70,000. 60,000 we have the train data. So what is the percentage? 60,000 upon 70,000. Please tell me, everyone. 6 upon 7.
80.85, around
85%, isn't it? Yeah. So 85% we have used for the train data and 15% we have used for the test data. Okay. And this train data will be using in the shape of the 60,000 28 by 28 by 1. You know, it means, can I say that this image will have the three dimension itself, and how many images we have? 60,000. So if you will consider in their original form, so what will happen? It will become four dimension. One dimension will be taking for the number of images, one for height of the image, another for width of the image, and another for the color, although it's a grayscale image. So what we will do, we'll just reshape it. And just for doing reshape, what we'll do, we'll just multiply this 28 by 28 by 1. What is the value, guys?
784.
784. So what will become the shape? It will become 60,000, comma 784. And now you see, at the row we'll have 60,000, and the in the column we'll have 784 column. Means it has becomes now the two-dimension data set. Then that just to normalize our image data, we need to represent. You need to multiply by 255 because your image are represented through 0 to 255. So just to normalize it, we'll just divide them into by 255. Okay, and that we are going to represent using the float 32. Means we are going to typecast it. And whatever data will be given in the label, that is the Y, we're going to represent them into categorical so that it can be used for the classification. That is we have done as a pre-processing of our data. Then in the case of deep learning, first we specify the model, then we compile the model. So while compiling this model, we have used the optimizer equals to RMS prop that yesterday we had used as the Adam. And the last function will be categorical cross and plot. So this is the architecture of the, this is the data that we have pre-processed, and this is we are compiling our model. Then after we are going to train this model on the trained data. Okay, just to take some less time, and just to improve the accuracy, you can increase the number of epoch. Yeah. So right now what I'll do, I'll just run it and say that instead of epoch equals to 12, I'll be taking epoch equals to 10. And let me run this. Okay. And friends, I tell you one thing, it will take some time. At least it will take around 10 minutes. So we'll just wait for it for the 10 minutes. So let me mute here, and I'll just wait for 10 minutes just to let it be complete. Meanwhile, if you have any question, then you can ask. So that since the batch size we have taken 64, the train image size is 60,000. So when you divide the 60,000 upon 64, it will become 938. So for the one epoch, we are getting how many iteration? 938 iteration we are getting. Okay, so I'm just going to mute my. Whenever you'll have question, you can ask me.
Hello, sir. Hello, sir.
Yes.
Sir, how this number of iteration is calculated as 938?
Parush, when I was discussing the deep learning primer, I told you. Now, again, I'm explaining, don't worry. See, iteration will be number of total data upon the batch size. So you see, the total train size is what? 60,000? And what is the
Yes, sir.
batch size? 64? So
Okay, sir.
60,000 upon
Now I
64.
get it.
It will become
Sir.
938. Okay, dear?
Okay, thank you.
Yeah. And I appreciate if you people ask.
Excuse me, sir.
Yes, Dipali?
Sir, I want to ask you regarding the project that we have to showcase on Saturday. So basically, if we have to show the what we have done, or
Yeah.
exactly.
Whatever you have done so far, I'm just going to check it out. That's it.
Okay, sir. Okay, sir.
Yeah.
Okay. That's what I just wanted to ask. Okay, sir.
So that at least I can see the speed of your implementation. No.
Yes, so because the data that is being given, so drawing the conclusion, because you have said that we have to do all the 5 steps. No, that's why I asked you
Exactly.
how much we have to, because the first thing that we need to is to figure out the business plan, basically the
Yeah,
business
Dipali, even I
statement.
tell you, I was expecting from each of you, but only you have asked. So at least, you have solved the purpose of everyone. So,
Okay.
yeah. So on Saturday, we are going to discuss it.
Okay, sir.
Yeah.
Okay, so that's why I just asked you, how much we exactly need to tell you that. That's why I just,
Sure.
because
Right.
the business objective only taking out, I think that will be the
Yeah,
tedious one.
business objective, and I just want to see whatever steps you have done as a part of data cleansing and ED.
Okay. Yes,
Yeah.
sir. Okay, sir. Okay, sir. Thank you so much. Thank
Okay.
you.
So we are at the
Sir,
10
I
epoch.
don't under-
Yes.
Sir, I don't understand what the optimizer is for.
What is the optimizer? Yuvraj, you were in the deep learning primer. I was talking about the gradient descent algorithms.
Yes, sir.
Yeah, and what is the job of the optimization? Just to update the weight, process it again so that we can get the minimum accuracy. Sorry, my bad. Maximum accuracy, minimum error.
Okay, sir, but there are lots of different optimizers. So how do we know what to use?
Okay, no issue. I'll tell you. Although I tell you one thing, Yuvraj, that is true that every optimizer may have their own specific use case. But if we are not aware, then what exactly we do? If we are not getting the appropriate accuracy, if you're not get the appropriate accuracy, we will just try with the multiple optimizer. We build the model with the multiple optimizer, and whichever gives us the maximum accuracy, we just finalize them. Guys, in the case of machine learning and deep learning, one thing you please remember, that is experiment. What should be the value of the parameter? Which model I have to use? Each and everything is basically your experiment. Yeah, that is experiment. You just try with each and everything. And whichever you'll be giving you the best, that will be the finalized. Okay?
Okay, sir.
Yeah, Yuvraj?
Yes, sir.
All right, so we have completed this 10 epoch, and you see on this 10 epoch, the accuracy that your model is showing on the trained data, it is somewhere 99.83. Yeah, let me do one thing. And when we have evaluated this model on the test images, then it is showing us the 99.04 accuracy on the test data. When we try it on the trained data, Then you see, it is giving us 99.80. And I tell you one thing. Whenever your training accuracy is very high, 99.80, and the test accuracy is 99.04. So in my case, the train accuracy is 99.80, and the test accuracy is 99.04. So what kind of model we have, Yuvraj?
So overfitted.
Right fitted.
Oh, sorry, right fit.
Yeah, both are high and very close to each other. Now another question. Suppose the test accuracy is 99.04 and the train accuracy is 100%. What kind of model we have? Again, there is a gap of only 0.96.
Sir, so it will again be right fitted.
No. It will be considered as overfitted. Because there is no any model which will not have even a single bit of error. There is no any model. So whenever you find it out that your train accuracy is going to be 100%, consider that overfitted model without checking anything else. Yeah, even if your model is giving you the accuracy of 99.99, this is the right fitted, because it is giving you the scope of 0.01% error. You cannot say that your model will always be 100% correct. You can never say. It should even give, even if it is giving the scope of 0.01, we'll consider it. But if it is saying that no, I'm 100% correct, means there is some error. Okay, guys. So this is how your convolution neural network works. We'll just stop here and let's meet tomorrow. And tomorrow we'll do the another thing. Okay.